All right, let's take a look at the homework that we had on page 51, please. Any issues with those two questions on page 51? Declan? I'm sorry? Yeah, number 2. All right. Number 2 says, the 1968 Corvette took 6.2 seconds to accelerate to 160 kilometers per hour. If it traveled 220 meters north during that time, find its acceleration. I went over this question a little bit, not in its entirety, but a little bit with somebody yesterday as they were doing it in seat work, and I can't remember if it was this class or the other class. But I know that one mistake that person made is probably a common mistake that a lot of you are going to make. It's a mistake that, honestly, if I was in your position in grade 11, I may have made that mistake as well, because it's one of those things that when you look at it, you know, we kind of think that this is there, but it's not really there. That mistake is that it doesn't say that it's starting from rest. We assume that it is often, right? It says it took 6.2 seconds to accelerate to 160 kilometers per hour. We assume automatically, for whatever reason, that it starts at rest, me included. But it doesn't actually say that. So we can't assume that VI is equal to 0 meters per second. How many people did assume that VI is 0? Okay. And you didn't get the right answer, eh? Yeah. So, honestly, if I read this question and I didn't see the answer, and I didn't see that people were getting the wrong answer when they assumed that, I might assume that as well, because it looks like it probably should be. But, in fairness to the people that wrote the question, it doesn't actually say that. So I guess the moral of the story is, if it doesn't say something, if it doesn't say it starts at rest, let's not assume that. Let's write down the givens that we do have. We've got a time here of 6.2 seconds, and we've got a final velocity of 160 kilometers per hour. We'll define north as positive. We're going to have to convert that, but we'll worry about that a bit later. The displacement is 220 meters. And we want to find the acceleration here. Let's convert the kilometers per hour to meters per second now. We say 160 kilometers is 160,000 meters. Divided by 1 hour is 3,600 seconds. 160 kilometers per hour is what in meters per second? 44 repeating. Okay, 44.44 repeating. Let's always go to 4 or 5 decimal places there before we round. When we get to a final answer, it's not important to go to 4 or 5 decimal places. In fact, we don't want to go that far when we get a final answer. But this is not a final answer, so let's not round it to anything less than 4 or 5 decimal places. All right, it's a group B problem, obviously. Which equation do you want to try for this group B problem? There's 5 of them. Any of them we can try. Which one do you want to try? Okay, minus 1/2 AT squared. All right, let's give that a try. We have the displacement. We have the final velocity. We have the time. The only thing we don't have here is the acceleration. So that looks like it's going to work for us. Got to rearrange that to solve for the acceleration, though. Remember the rules? It was a week and a half ago that we had that little lesson on rearranging equations. The first step was what? We want to solve for A. The first step was getting rid of what's not attached. Good. What's not attached to the A there? VF times T, right. So how do we get rid of VF times T? Add them to the other side? No. Subtract them, yeah. We say VFT minus 1/2 AT squared, but the VFT is not subtracted. So we don't add it to the other side. It's a positive value, so we subtract it from the other side. Let's say D minus VFT equals negative 1/2 AT squared. Now we want to get rid of the negative 1/2 and the T squared. How do we do that? We can divide it. So let's say delta D minus VFT over negative 1/2 T squared. Now we could simplify this a little bit if we wanted to, make it look a little tidier, a little bit neater, but we don't have to. And that's a correct rearrangement of that equation here. Let's plug in our numbers in. delta D was 220 minus VF times T, which is 44.44, times a time of 6.2 seconds. All right, let's make sure that we're doing this in steps now. Okay, let's, on your calculators, go 44.4444 times 6.2. Do that first. Do the multiplication there first. What do you get for that? 44.44 times 6.2. What is it? 275.55. All right, let's go 6.2 squared times 0.5. What's 6.2 squared times 0.5? Negative 19.22. It's a negative, right? Because there's a negative up front there. So now let's say 220 minus 275.555 is going to give me negative 55. Divided by negative 19.22. Negative 55 divided by negative 19 is going to give me somewhere in the range of 2.89. Okay, thank you. 2.89 meters per second squared. It's a positive value. What does that tell us? It's speeding up, right? And of course it is. The question says it's accelerating. It's speeding up to 160 kilometers per hour. So of course we should get a positive value. Sometimes when we're going through the question, we see some negatives kind of tossed in here, like right here and right here. We start getting a little nervous that we're going to get a negative value, but in the end it works out. It always works out the way it's supposed to, unless you make a mistake in there somewhere. Does that make sense? So what was the problem with that question? Was it the whole initial velocity thing? Yeah. Like I said, I might have made the same mistake. If I didn't know better, then I might have made the exact same mistake as you did, because it looks like it should be VI is equal to 0, but clearly it's not. All right, let's try one more example here. This will be our last example on this stuff for a while. It says a bullet accelerates the length of the barrel of a gun 0.750 meters with a magnitude of 5.35 times 10 to the 5 meters per second squared. So that's a pretty high rate of acceleration. With what speed does the bullet exit the barrel? With what speed does it exit the barrel? Something's 0.750. Something is 5.35 times 10 to the 5. What's the 0.750? What do we call that? We're going to call it displacement. Good. What about the 5.35? It's going to be the acceleration. Good. We're looking for what? What speed is it? V, VI, VF? It's going to be the final speed, right? We're looking for VF. Is there anything else we have if we read between the lines here? Anything else that we have? Sorry? VI is what? Right. It doesn't actually say that the bullet starts at rest, but we know that a bullet always starts at rest in the barrel of a gun, right? Unlike a Corvette, isn't always, the beginning of a problem of a Corvette isn't always at rest, right? It accelerates to 160 kilometers per hour. Well, maybe it was traveling down the highway when it did that. Okay? This bullet, as it travels the length of the barrel of a gun, must be starting at rest as it begins to travel that length. So we're going to say VI is equal to 0 meters per second. Which one do you want to try? Which equation? The one with what? Well, there's a number of them that have velocity in them, and we can solve for velocity, and as long as it's not changing direction, it'll have the same value as speed, so that's okay. Okay, right? Okay, let's try that one. VF squared is equal to VI squared plus 2AD. In the end here, VI is 0. So we can actually cross that off to simplify it a little bit if we want to. And then we want to solve for VF, so we're going to take the square over by square rooting. It's going to be the square root of 2 times 5.35 times 10 to the 2 times the displacement of 0.750 meters. Let's get what's underneath the square root sign first, and then let's square root it after we get that. 633 meters per second. Is that a reasonable speed for the speed of a bullet as it leaves the barrel of a gun? Sure it is. It depends on the gun, but that's a very reasonable speed. So, sounds right. Oh, you got a different answer? 802? 802 is also reasonable. Just because it's reasonable doesn't guarantee that we're correct, but it's a pretty good indication usually. A bunch of people get 802? 928? All right, let me take a look at it with a calculator here. 1 second. All right, the answer is 895, but the problem is, I wrote this down wrong. It should be 5.35 times 10 to the 5 meters per second squared. When we do that math, we end up getting 896 meters per second, which is obviously a lot faster than the answer we had, but still an entirely reasonable number for the speed of a bullet as it leaves the barrel of a gun. Can everyone get that now? Everyone's getting that? All right, take a look at these ones for the next couple minutes, see how they go. And I want to take a look at question number 1. There were a number of people that, not necessarily struggling with question number 1, but had a couple of issues with question number 1. Maybe didn't even realize they did until they looked at the answer and saw that the answer was negative 2.4 instead of positive 2.4. So I want to go over question number 1. If you're not done question number 2, I'll leave you with question number 2 to finish up for homework tonight. Number 1 says a jetliner lands on a runway at 70 meters per second, reverses its engine to provide braking, and comes to a halt 29 seconds later. We know right away that this is a Group B problem, even before we look at what we're looking for, even before we see what we're asked to solve for. It's Group B because it slows down, comes to a stop. Tell me what the 70 meters per second is. It's the initial velocity. Tell me what the final velocity is. 0. We've got a time here of 29 seconds. We're looking for the acceleration, and question B is a little bit different. What length of runway did the jet require? What are we really looking for in question B? The displacement, right, the displacement of this jet plane as it's traveling down the runway. Now, most people that I saw did A is equal to delta V over delta T for the first question, A, and that's probably what I would have done as well. Delta V, however, is not 70, as a number of you guys said. Delta V is what? Why is it negative 70? 0 minus 70, final minus initial. A number of people said V over T. Now, I've told you guys a number of times here over the last couple of weeks that we want to be really careful about writing things down the way they're supposed to be written down. A lot of times we can get away with shortcuts for getting a vector sign. A lot of times we can get away with shortcuts for getting a delta sign. It just works out for us a lot of times, but sometimes it doesn't. This is one of those cases where it doesn't. If you write down A is equal to V over T, then you're going to go 70 over the time, 29 seconds. You're going to get the wrong answer because you're going to make it a positive, and that's not right. So you've got to write it down properly to catch the fact that it's supposed to be 0 minus 70, and therefore it gives you a negative answer. When we do the math, it should work out to be negative 2.4 meters per second squared. Now the second part of the question, what length of runway is required? There's a number of equations that I could use now. I could use d is equal to VIT plus 1/2 AT squared. I've got everything in there, including the acceleration now. I just solved for that. I could use d is equal to VFT minus 1/2 AT squared because I've got that. I could use VF squared is equal to VI squared plus 2AD because I've got everything there except for D. I could use D is equal to vi plus vf over 2 times t. That's the one that I'm going to use. It's not really any better than the others, but I'm going to use that one simply because it does involve acceleration, simply because it doesn't have acceleration in there. The only reason I'm choosing that, look, if I've made a mistake on acceleration, it's not going to carry through to the next question. If I use one of the other equations and I've made a mistake on the acceleration, it will carry through. Does that make sense? Doesn't mean it's a wrong strategy. You can do that. You can use this number in your other equation. But if I don't have to, I'm not going to, just in case I've made a mistake on it. So what do we got here? 70 meters per second plus 0 over 2 times the time of 29 seconds gives me a displacement of 1,000 meters or 1.0 kilometers. 1.0 times 10 to the 3 meters or 1.0 kilometers. Is that good? Okay with that? All right, I see a couple of people still writing, so I'll give you a second to do that, and then we'll move on to the next little thing. All right, your homework for tonight, please. Don't worry, you don't have to do them all. Your homework for tonight, page 53. Write down these ones that you have to do. Page 53, number 1, 2, 3, 4, 5, 6, 7, 8, and 9 to 14. Well, no, it's not all of them. Oh, it is all of them. Yeah, sorry. Yeah, you're right. Yeah, you're right. You're right. It is all of them. I'm sorry. So questions 1 to 14, please. We'll try to give you a few more minutes to work on them here before the end of class, so that it's not, all 14 questions here for homework tonight. Okay? Yeah, it is. If you don't have any class, time to do it. Yeah, it is. You're right. All right. Look at this. This looks important. It's big letters, really big letters. We're going to start looking at velocity time graphs here today. A velocity time graph has what on the x-axis, what on the y-axis. We know by the title of this. Tell me what's on the x-axis. Time. Time is the manipulated variable. Velocity would be the responding variable. Velocity would go on the y-axis. Time will go on the x-axis. There are a number of shapes of velocity time graphs that we will see, similar to the position time graphs, but different meanings. Tell me what this one would mean. Velocity as a function of time with a straight horizontal line. Tell me what this one would be. No, not displacement. I mean, there is displacement happening, but tell me what the meaning of it is. Connor? Yeah, is it stopped? Is it stopped? It's going at a constant velocity. It's not stopped. If this was a position time graph and it was a horizontal line, it would be stopped. But this isn't a position time graph. Okay, the position here isn't changing. The position here is changing. The velocity isn't changing. So we're going to say this one is a constant velocity. Boy, it's easy to get them mixed up, Connor. Like a position time graph, velocity time graph, they look exactly the same except for that y-axis. Exact same shape. But you have two completely different meanings. The next one has an increasing line, or a line that's sloped upwards. If this was a position time graph that was sloped upwards, what would it mean? Right here? Position time graph? Not acceleration, Connor. That's a constant speed or a constant velocity. Whoops. Can't spell it, but. Well, what's this one mean then? It's accelerating. It's not a constant velocity. Look, At the beginning, the velocity is 0. Then it increases. Then it's a bigger number for velocity. Then a bigger number. It's an increasing velocity. So in other words, it's accelerating. It's a uniform acceleration. That means it's a constant rate of acceleration. We know that because it's a straight line, but it's still accelerating. How about this one? It's also a straight line, but this time it's sloped downwards instead of upwards. It's deceleration, yeah. If this was a position time graph that was sloped downwards, it would be a constant negative velocity. That's not what we have. This velocity is changing, it's decreasing. This would be a negative acceleration. Or in other words, a deceleration. It's slowing down. Now, understand it's still moving in the positive direction. It's not going backwards. Like this one was going backwards. This one's not. The velocity at any of these points is still a positive value, but the velocity is decreasing towards 0. What about this one? If it was position time graph, it would be accelerating. This one is also accelerating. But it's not accelerating at a constant rate. It's an increasing rate of acceleration. It's like you put your foot on the gas pedal at a stop sign to take off. You put your foot on the gas pedal just a little bit and then you kind of ease onto it. You accelerate the whole time, but as you're easing onto the gas pedal and putting your foot further and further down, you accelerate more and more and more. Not only are you traveling faster, but the rate at which you increase your velocity is increasing. You put your foot on the gas pedal just a little bit, you'll accelerate. Put your foot on the gas pedal a lot, you'll accelerate more. Easing your foot downward on the accelerator would be described by this graph where your rate of acceleration is changing. You're increasing your rate of acceleration. The rate of change of velocity is increasing. How quickly you're doing it is increasing. If you take a look at this, you don't have to draw this out if you don't want. It's just to illustrate what's happening here. Look, in this amount of time right here, they call it 1 second. My change in velocity is a little bit. 1 second over here, the same amount of time, look at my change in velocity now. So during the same amount of time, how much my velocity has increased quite dramatically. So the rate at which I've increased my velocity has increased. In other words, my acceleration itself, it's accelerating the whole time, including down here, but the acceleration itself is increasing as we progress through time. What about this one? Slowing down? I heard somebody say slowing down, I think. If it was a position time graph, this would mean slowing down. This is not a position time graph, it's velocity time. What does it mean? It's decreasing acceleration. This one's a little bit confusing. People always have a little bit of trouble with this one. Is the velocity increasing? Yeah, it's speeding up. It's speeding up. It's not slowing down. But the rate at which listen to this one, it sounds kind of odd, but the rate at which the velocity increases decreases. It's not the velocity that's decreasing. It's increasing. But the rate at which it increases is decreasing. In other words, the acceleration is still there, but the acceleration is getting smaller. It's speeding up, but not as quickly as it was before. This one would be like you've got your foot on the floor, gas pedal, right, pushed all the way down, and then you ease off. You still speed up, but you're not speeding up as quickly as you were before when you had your foot on the floor. So it's going to be a decreasing acceleration. Still speeding up, but not as quickly as it was before. This diagram here, again, you don't need to copy unless you want to. Again, it illustrates exactly what's happening there. And say 1 second, the change in velocity is this much. 1 second down the road, the change in velocity is this much. If the change in velocity is quite a bit smaller than it was during the 1 second before, then the velocity, the change in velocity is decreasing. Not the velocity, but the change in velocity is decreasing. Does that make sense? Yeah, this one always gives people a little bit of trouble. So if it doesn't give you trouble, if you understand it, then that's great. Perfect. Let's define acceleration. We've already defined it, right? We've already defined it. It's way back before we did our equations. It's the rate of change of velocity of an object. If it was the rate of change of velocity, then it's described by the equation a is equal to delta v over delta t. But if I take a v versus t graph, let's say it's a straight line, v versus t graph, and I go delta v over delta t from that, what am I really doing? I'm doing the slope, right? So the definition for the acceleration, which we learned a week ago, or almost a week ago, translates directly onto this graph right here. The slope of this graph ends up being equal to the acceleration, and I can find it by delta y over delta x, or rise over run. You know, I think we'll wrap it up there. I think I'll give you a chance to work on the questions that I assigned for homework. We'll wrap it up here, and then we'll move on tomorrow on the velocity time graphs. All right? So what's your homework for tonight? Check and reflect, page 53, number 1 to 14. You've got about 12 minutes now, so you should be able to get a few of those questions done. Please finish up the rest of them for homework tonight.